Hi, I am Vishak, PhD student at IIT Bombay. In this session, I will be giving an overview of our work speeding up neural architecture search using adaptive subset selection. This work was done in collaboration with Abacus AI. Neural architecture search deals with the problem of finding the best neural architecture given a search space of operations and some amount of data. Earlier methods to solve NAS problems were based on evolutionary methods, RL-based methods, Bayesian optimization, etc. All these methods took a lot of time to find the best architecture. Recently, a lot of work is being done on how we can select representative subsets of data such that the training time is reduced without compromising the accuracy of the model. We are particularly looking at adaptive subset selection, where we adaptively find subsets, that is, as training progresses, based on the current parameters, we select the most important subset of data. Before going on to our work, let me give a brief about SuperNet-based neural architecture search. SuperNet-based methods formulates the task of neural architecture search in a differentiable manner. In DARTS, that is differentiable architecture search, the authors gives an algorithm for differentiable neural architecture search. In this method, the search is for a computation cell which forms as the building block of the final architecture. A cell is a directed acyclic graph consisting of n nodes. Each node is a latent representation like a feature map. Each edge is an operation. We want to find which operations would be the best between two nodes. The edges are given weights, and the task of architecture search becomes learning the weights. After training, we get some values for these weights, and we can select the edge with the maximum weight. The goal of architecture search is to find the supernet parameters alpha star that minimizes the validation loss, where the weights W star are obtained by minimizing the training loss. This bi-level optimization problem is shown here. In the paper Rethinking Architecture Search in Differentiable NAS, the authors stated that alpha, the edge weight, may not represent the operation strength. This leads to the algorithm preferring certain kind of operations. The strength of each operation on a given edge is defined as how much it contributes to the performance of the supernet. Here, the operation strength is calculated as follows. Each operation edge is masked out, keeping all the other operations, and re-evaluate the supernet. The one that results in the largest drop in the supernet validation accuracy is considered the most important on that edge. Next, we look at adaptive subset selection algorithm by Kill and Shetty et al. We select a subset of training data based on the current parameters such that the loss on the validation set is minimized. In the inner loop, we fix a subset of data and minimize the loss on the training data with respect to the model parameters. In the outer loop, we fix the parameters and optimize on the subset. In this slide, we will give a brief about our approach, adaptive DPT. We study how a supernet-based NAS algorithm can be made more efficient using an adaptive subset selection algorithm. We propose adaptive NAS, a mixed, discrete, and continuous bi-level optimization problem. Adaptive NAS reduces the runtime needed for supernet-based NAS algorithms with no decrease in final accuracy. In our method, we use DARTS PT as the supernet-based base model and adaptive subset selection based on Glister algorithm. We design a bi-level optimization problem. Inner optimization is keeping the subset of the data and the supernet parameters fixed and optimizing on the model parameters theta. Outer optimization is on the subset as well as on the architecture parameters while keeping the model parameters fixed. Next, we give a brief about the experiments that we performed. Experiments were mainly on the NAS bench 201 search space with datasets CIFAR10, CIFAR100, ImageNet 16, 120. Experiments were also performed on other search spaces like DARTS S4 with CIFAR10 dataset. We briefly go over the baselines that we used. First one is DARTS PT, the original paper. Second approach is DARTS PT RAND, where we take just 10% of the training data and train the DARTS PT model. Third approach is based on the paper Accelerating Neural Architecture Search via Proxy Data by Nayak et al. This approach, DARTS PT entropy, first selects subset based on 5 different approaches. Random is basically selecting random data, random training data. The authors then select training data based on entropy of the data point. Basically, top K entropy points to the data points having maximum entropy, K data points having maximum entropy, and bottom K refers to the K data points having minimum entropy. Forgetting events refers to the data points that were misclassified the most during training time. For K center, the authors used pre-trained data embedding. Select K examples based on greedy K center algorithm. The findings of these papers are: when a small number of examples are selected, easy examples are to be selected for the maximum performance. When the easy examples are already selected, adding middle and difficult examples gives the maximum performance for a subset selected. We introduce another baseline called DARTS PTFL. Subset is selected using facility location problem, which is similar to the K-medoid clustering. We use the submodlib library by Koshal et al. For the implementation of the facility location based subset selection approach. Next, we look at some of the results from our experiment. In all these experiments, we use 10% of the data. The results show that using adaptive subset selection for supernet based approaches, the accuracy can be improved a lot, while the time can be reduced a lot. For example, for CIFAR10, the accuracy was gained 5%. At the same time, the time was reduced 8 times with just using 10% of the data. We also performed experiments on hyperparameter optimization approaches. We use methods DEHP and BOHP, and we use adaptive subset selection algorithm on MNIST dataset. We found that the accuracy can be improved with just using 20% of the data while reducing the training time. For the future work, we use subset selection for super tickets, where the combination, the process of neural architecture search and pruning are combined. In conclusion, Adaptive subset selection methods can complement neural architecture search algorithms. For NAS Bench 201, we achieved 94% accuracy on CIFAR 10 with just 10% training data in 45 minutes. Thank you.